Hello, we're back for more triple integrals. This time we're going to be working with cylindrical coordinates, which we already kind of got a sneak peek to in the previous section. But now we're going to come right out and call them cylindrical coordinates. So the deal with cylindrical coordinates is that one of your variables, typically z, gets to just be z, while x and y will have some sort of circular relationship, and so we switch our x and y over to r and theta. What we saw before, just to bring it back to life again, was, for example, in this problem, number 5 from 15.6, we saw a situation where x got to be x while y and z had a polar relationship, and we could switch those over. And then in example 5, we saw a similar scenario where y was the variable that got to just be y, and then x and z had a sort of circular relationship, right? We had this xz plane, we had a circle we were integrating over, and we were able to switch it to polar. So given that, what's really going on with cylindrical coordinates is it's like a three-dimensional polar coordinates, where that third dimension remains in rectangular, but then the other two dimensions have a circular relation, so we switch them to polar. Okay, well, it's really nice if we can have like a standard consistent way to switch over to cylindrical coordinates, and we are going to do that. However, I want you to remember the examples that we did in 15.6 where things were not the same, okay? Now, what typically happens in cylindrical is that we use our polar coordinates, r and theta, for the x, y part of the coordinate, and then we move vertically by z. Okay, so z gets to be itself. You're going to have functions, z is going between, and then x and y are going to be replaced by r and theta. We still have the same rules. R is a radial arm, so it is always positive. Theta is typically running between 0 and 2 pi, some portion of that. However, there is nothing saying actually that theta has to be positive. You could see things, for example, like minus pi halves to pi halves. It just depends on the shape that we're working with and where it's located in space, okay? We have the exact same conversions as well. X is our cosine, y is our sine, z gets to be z. So that's the big difference right here is we've added in this part, okay? But there's no change. Z just gets to be z, okay? Tangent of theta is still y over x, and x squared plus y squared is still r squared. Now, if you recall, before we had a situation where we had our dx, dy would switch over to r dr d theta. So now we want to see, well, what happens if we have this third variable, z, where z just gets to be z. So we're going to look at the Jacobian of x, y, and z. And remember that x is our cosine theta, y is our sine theta, and then z is just z. So the Jacobian is a determinant, and it takes the first variable's first partials in the first row. So if x is our cosine theta, and we have three variables showing up here because we actually have r, theta, and z, I need the first partial of x with respect to r, with respect to theta, and with respect to z. Now, I get something for the first partial with respect to r. I get cosine theta dr. And for the partial with respect to theta, I get minus r sine theta d theta. But because there is no z involved in the equation, x equals r cosine theta, the first partial with respect to z is just 0. And a similar thing happens for y. Y is r sine theta. We get our first three partials, y sub r, y sub theta, y sub z, and that y sub z is just 0. And then something similar happens for z. Z is just z. There is no theta or r involved, so the first partials with respect to r and theta are 0 and 0. And then with respect to z, we just get 1 dz. So we can calculate a determinant on this. I chose to do an expansion about the third column, and so that's plus minus plus on there. So I had a whole lot of zeros because first I looked at 0 times the determinant of, let's see, the 2 by 2 that is not in its row or column. So that gave me a big fat 0. Then I did, let's get some of this stuff erased. Then I did minus 0 times another determinant, and that just gave me 0. Okay. And then the final one was plus 1dz times the determinant, the 2 by 2 determinant of the components that are not in the same row or column as 1dz. And so that's where I started to get some non-zero stuff. In particular, I get r cosine theta dr, r cosine squared theta dr d theta. And I get minus a negative, so plus r sine squared theta dr d theta. They both have a dr d theta in common, so I factored that out. This dz could also join the dr d theta. And then cosine squared plus sine squared with an r multiplier in there. We factor out the r, we're left with cosine squared theta plus sine squared theta. Remember, that is just equal to 1, so that whole thing is just equal to r. So it turns out that the only difference in dv from polar is that we have the dz in there, okay? So hopefully that's not a surprise because we weren't actually messing with z. We messed with x and y and turned them into r and theta. All right, now our triple integral, when we convert everything, we have to replace all x's with r cosine theta, all y's with r sine theta. We need to replace our dx, dy, dz with r dz, dr, d theta. Now the order is dependent on how you set things up and what sorts of functions you're integrating between, okay? Typically, the innermost integral will be your z value, your z functions, and they will be functions of r and theta. So you'll have a lower bound function in r and theta and an upper bound function in r and theta. And then your middle integral will be this one, h1 of theta, h2 of theta. So it could be that r goes from a constant to a constant, but r could also go from a function of theta to a function of theta. Whereas theta in this particular case is going from alpha to beta, where those are just constant radian values. Okay. Now, of course, any one of these could just be constants, and we could switch the order depending on what functions or what variables are functions of other things. Okay. We're going to start off with a little bit of, not really a review, I guess this is a bit of a build up on something that you did in Calculus 2 when you were first introduced to polar coordinates. One of the things that you all had to do was to convert rectangular coordinates to polar coordinates. We're going to convert rectangular coordinates to cylindrical coordinates, okay? So in this particular case, I have an x, y, and z point, and I want to convert it to cylindrical coordinates. Cylindrical coordinates, just to recall, is r, theta, z. So I'm after a point that is modeled by r, theta, z. Now I've got all my conversions up here. I know x is r cosine theta, y is r sine theta. Those aren't helping me. Z is z. Oh, okay, well that's easy. I'm not going to change z. Tangent of theta is y over x, and then x squared plus y squared equals r squared. I think those are the ones that are going to help me. So I have tangent of theta is equal to y over x, which means theta is tan inverse of y over x. And then we also have r squared is equal to x squared plus y squared. So we're going to use those in order to figure out how to plot this or what the point actually is. Now, let's see. So for theta equals tan inverse of y over x, we're looking at tan inverse of -1 over -1. Now we need to be really, really careful because we have a double negative and those are going to divide out and become positive. But what we should not forget is where -1, -1 is located in space. It's over here in the third quadrant. So if I was to spin around, my theta is actually in the third quadrant. But if I was to plug tan inverse of 1 into my calculator, I'm going to get pi fourths. That's just what my calculator will give me. Clearly, my point is not at pi fourths, okay? So I need to add pi to get to the third quadrant. So that means theta is equal to pi over 4 plus pi, which would give me 5 pi over 4. So that's my theta value. Okay, and that makes sure that I'm in the right quadrant for x, y, and of course z would take us to octants, so it'll make sure I'm in the right octant. Now r squared is x squared plus y squared. We're going to take the x and y values in here and we're going to square them. -1 squared plus -1 squared is going to give me 2, which means r is always positive. It's going to be the positive square root of 2. So what that means is that r theta z is equal to square root 2 for r, 5 pi over 4 for theta, and -3 for z since z didn't change at all. And that's how I deal with that. Now the second problem is to do this, to go in reverse. In the second problem, I'm given r, theta, and z are 2, 3 pi over 4, and 3. And I want to go to rectangular coordinates, which is what we're familiar with, x, y, z. So I need to convert, and I have r and I have theta, and I'm thinking, you know what? I remember x is r cosine of theta. And I have r and I have theta, so why don't I just plug those in and see what I get? All right, well, this is going to give me 2 cosine of 3 pi over 4. 3 pi over 4 is going to be in the second quadrant, and so cosine of that is going to be a -√2 over 2, which simplifies to a -√2. All right, so I have my x value. Y is equal to r sine of theta. And again, r is 2, and we're looking at sine of 3 pi over 4. In the second quadrant, sine is positive, and so this gives me 2 times the square root of 2 over 2, and that simplifies to just be the square root of 2. Z is z. Z doesn't change. So I have my coordinates. X, y, z is equal to -√2, +√2, and 3. And that will get me a point in rectangular coordinates that is the exact same point as the cylindrical coordinate that we started with. All right, that's how you go back and forth between the two. There are a couple of homework problems that make you do this. I will say that it's not like the be-all, end-all. It's just important to be able to go back and forth, but it's not... I wouldn't say it's like 100% necessary in order to go through the integrations, but it's still important because it builds some of the necessary skills for the conversions. All right, next one. We're going to describe the region bounded between two cylinders. X squared plus y squared is 1, and x squared plus y squared is 9. And between the planes, z equals -1 and z equals 4, with x greater than or equal to 0 and y greater than or equal to 0. And we want to describe these using cylindrical coordinates. Okay? What we're wanting is an inequality form for r and for theta and for z. Now, these cylinders are circular cylinders, and they run parallel to the z-axis. So these are standard upright cylinders. One has a radius of 3, one has a radius of 1. So we could picture this in such a way, something like this. Oops, that should be dashed. Okay, so we have the region that's bounded between the two cylinders. That's going to be this region outside the smaller cylinder and inside the bigger cylinder. Okay? Well, let's see. If I was to draw an axis on this, It doesn't go all the way down, just part way, because down here is z equals -1, and up here is z equals 4. Okay, I can clearly see that my z values go between -1 and +4. So that's the easy part. -1 is the lower bound for z, and 4 is the upper bound for z. Now my R values are, it's outside of the unit cylinder and inside of the cylinder with radius 3. So we're here. And it looks like we're going to go from a radius of 1 up to a radius of 3. That will take care of that donut-like shape. And then I drew this so that it was in all 4 or all 8 octants, really. But I have this little stipulation right here. It's saying that X and Y are positive. And what that means is that we are in the 1st and 5th octants. Because Z can be negative, and it is negative, in fact. But what that means, this gives a restriction on theta. And the restriction that it gives is, think about just the XY plane. If we could only be in the 1st quadrant, then our angle would be from 0 to pi-halves. That's the same here. So lower angle is 0, upper angle is pi-halves. And these are the coordinates that describe the shape that we have here, which is kind of crazy to be given 3 inequalities. Each of the inequalities is a variable trapped between 2 constants, and it gives us this cylindrical donut-like shape. Kind of cool. All right, so if we had to integrate over something like that, I already have our bounds written out. And so that's kind of the point of this exercise, is to, if you've been given a region, you need to know how to define your bounds for r, theta, and z so that you can set up an integral to integrate over the region. All right, before we get to integrals, though, I want to describe a few regions. The first one is z equals r, and honestly, I don't know what that is. Not in cylindrical. I'm not familiar with it enough. And so when I'm working with cylindrical coordinate equations, I convert them to rectangular in order to find something that's familiar for me. So we're going to convert to rectangular. And when I convert to rectangular, I have to remember that r is equal to the square root of x squared plus y squared. So that means that z is equal to the positive square root of x squared plus y squared. Well, from all the work that we've done on being able to identify what an equation is in 3D, this comes from chapter 12, this is the top half of a cone. That's it. It looks like this. It does extend forever, but we can't draw forever, so we just draw a non-infinite cone. But it looks about like that. That's the top half of a cone. Well, let's look at what z equals r squared might be. So z equals r squared, we have to remember that r squared, we can convert that to rectangular, and it is x squared plus y squared. So this gives me z equals x squared plus y squared. Okay. If I was to, kind of examine this in one variable at a time, like z equals x squared is a parabola, and z equals y squared is a parabola. And putting those all together, this gives me upward facing paraboloid. And we would draw it, we could draw it kind of like this. I'm drawing terrible drawings. They're all shaky and everything. I think it's my pen. I'll blame my pen. Okay, so there's my paraboloid. It's upward facing, I know, because I just did the little cheat where I focus on one variable at a time, like z equals x squared. I know that that's the equation of a parabola. And then I focus, oops, I don't do that. How do I go back? I don't. Let me go ahead and redraw that. Okay, then I focus on z equals y squared and ignore the x squared, and I have another parabola. Okay, so that's kind of one of the tricks that you can use. And the idea behind that is kind of like a projection, but also like a level curve. And these are some of the words that we used in 12.6 and then in 14.1 when we were learning about graphing and identifying three-dimensional shapes. Okay, next one, C, we still have Z and R involved, but now it's Z squared equals R squared. So that means Z squared equals X squared plus Y squared. Now check this out. If I was to take the square root of this, it'll start to look familiar. Z is equal to plus and minus the square root of X squared plus Y squared. That's the top and bottom half of a cone because I have the minus in there as well. So to draw that, I draw a big X, and then I make it circular on top and circular on the bottom, and then I throw in an X, Y, Z octant, and there's the top and bottom half of a cone. So we call that a full cone. All right, Z equals theta is interesting. Because R is not involved in the relationship that's written here, this is independent of R, and that means that R goes from 0 to infinity. But what we're going to do so that we can actually kind of get a picture of this is we're going to imagine R being between 0 and 1, but we have to remember that R is just simply greater than or equal to 0. I'm just fixing it for a short radial arm because otherwise I can't draw this. And if I can't draw it, then I can't identify it. So what's happening here is, let's see, put that aside. As theta increases, so does Z. Okay? So if we were to try to draw something like this, this is not going to be very accurate. I'm just going to kind of do half a job here. If theta is 0, then the height Z is equal to 0 as well. As theta increases, though, what's going to happen, oops, okay, hold on. So Z is 0, but remember our R value is going from 0 to 1. Okay, so there's our radial arm, okay? Remember R is actually infinite, so this radial arm actually goes on forever. We just fixed it, okay? That's it. Now that we're fixed out here at R equals 1, as theta increases, so as theta starts to swing around, Z is also increasing. And the way I can kind of show that is to show the twirls that are coming out of there. Now, here's an even better thing to do to try to make this more clear. So I've got all these radial arms that kind of sweep out and fill in the space. Hard to see it, but what this is, it's like a spiral staircase or a spiral slide with infinite length. And by length, I mean that radial arm R. And another name for this is a helicoid. Okay, kind of weird. I don't think that one's very intuitive. I can do it easily because I've done this before. This is brand new for you, so I would say it probably won't be easy to see that. And that's why we do it here. All right, theta equals pi thirds. This equation is independent of r and theta. I'm sorry, r and z. Okay, so we have infinite height and we have infinite radius here. Okay, but theta is fixed at pi thirds. So let's see what that looks like. Theta is the positive angle made with the x-axis. So if I was to sweep out by pi thirds, I would be about right here. And then I could draw a line. We can assume that this line goes on forever, okay? Because our equation is independent of z, I know that this line needs to now extend and run parallel to z. So we can do that way. And then we can connect with the z-axis here. Let me draw that a little longer. Oops. Okay. Get in my theta is pi thirds here. Now, this is a plane. It doesn't move. It stretches up and down infinitely, and it stretches out along the the first octant and fifth octant infinitely. So it's an infinite half plane. And it's called a half plane because it's not going to cut through to the third octant, third and seventh octant, because the radial arm r is positive. Okay. Now I will admit that some people like to bicker about that one and say that this plane would extend into the third and seventh octants. But by definition, if your radial arm is only positive and your angle is pi thirds, then this can't extend beyond the z-axis. It can only come out through the first and fifth octants. Okay, so it is an infinite half plane through theta equals pi thirds. Okay, so that's our lesson on converting from rectangular to cylindrical, cylindrical to rectangular, and then taking some cylindrical equations and trying to identify them in rectangular and give them a name. Now we want to set up some integrals, okay? In this next problem, we're going to let E be the solid that's enclosed by the paraboloids z equals x squared plus y squared, and z equals 8 minus x squared minus y squared. And we're going to write this triple integral over E of x, y, z dv as an iterated integral in cylindrical coordinates, okay? Our solid is enclosed by these paraboloids. And I'm hoping right about this moment you're realizing why I was harping on three-dimensional shapes so much all semester. It's because if I can't draw this, I'm kind of out of luck here, okay? I've got to be able to figure out which one of these paraboloids is on top and which is on the bottom. Okay, so z equals x squared plus y squared is upward facing. I know that because there are no negative signs in front of the x squared and y squared. That means z equals 8 minus x squared minus y squared is downward facing. So what we have here is a downward facing paraboloid. Okay, that's my z equals 8 minus x squared minus y squared. And then we have an upward facing paraboloid, and they intersect. Okay, you have to imagine that these paraboloids are actually continuing on forever, but there is a point at which they intersect. And they actually intersect all the way around here, because the bottom paraboloid is going to cut through the upper paraboloid, okay? And then the space that's enclosed by the paraboloids is all of this in here. All the stuff above the orange paraboloid and below the purple paraboloid. And the orange paraboloid is the z equals x squared plus y squared. Okay, now we need to get the equation of intersection. I don't know if you can see this, but the shape of this solid is kind of like an acorn. And that belt, the blue belt where they intersect, is the widest part of the shape. And so if we were to shine a light from the top onto the XY plane, we would get a circular shape that has the same size as that intersection loop. So we need the equation of that intersection. To find it, we have to take the two paraboloids and set them equal to each other. So we're going to solve 8 minus x squared minus y squared is equal to x squared plus y squared. If I move all the x squared and y squareds over, I get 8 is equal to 2x squared plus 2y squared. If I divide everything by a 2, I get x squared plus y squared is equal to 4. Okay, so what we have now is the ability to figure out our region of integration in the x and y variables. Okay, so what we have here, this intersection, is a circle of radius 2. Just draw a very simple one, and that's good enough. So this is x and this is y. Okay, now, so circle of radius 2, and it's a full circle. We have nothing saying that we are going to restrict to any octant or anything, and so it's a full circle. All right, now I want to get some an octant on here. Okay, we need to get the z-bounds. Okay, remember the whole idea of we have the floor and the ceiling. We need a floor and we need a ceiling for z. It looks like the floor is the upward facing parabola. So the floor is z equals x squared plus y squared, and the ceiling is going to be the z equals 8 minus x squared minus y squared. Okay, so when we set up our integral, we have the triple integral, write this closer, over e of xyz dv is equal to a triple integral, and I've got to fill in the blanks now. Z is going from x squared plus y squared up to 8 minus x squared minus y squared. X and y, well, we can define those as being the circle x squared plus y squared is less than or equal to 4. It's kind of a strange notation right there, but we often use that notation in this textbook in order to declare like what's going on with the x's and the y's, okay? And when we see that, we know that we can switch to polar. That's the point. And polar in 3D is cylindrical, okay? And so we still have the x, y, z, and then we're going to have a dz and a dA. Okay, so we've got to fix that dA. We've got to fix the x squared plus y squared is less than or equal to 4. In other words, we need to switch over to cylindrical. Okay, so I need to fix everything in here. For dz to polar, my bounds now, instead of having x squared plus y squared on the bottom, I have r squared is less than or equal to z, which is less than or equal to 8 minus r squared. That is the conversion of this integral to polar. Okay? Then we have the dA to polar, and that's where we have x squared plus y squared is less than or equal to 4. We have a full circle. The circle's of radius 2, so that tells me that r can go from 0 to 2, and that tells me that theta can go from 0 up to 2 pi. And these are the inequalities that describe the region that we're trying to integrate over. So now I can switch over to polar everything. Have to remember, in the integrand, x, y, z also needs to go to polar. So that's going to be r cosine theta, r sine theta, and then z, which becomes r squared z cosine theta sine theta. Okay, last thing is dA. In polar, we're going to have r dr d theta. Okay, let's pop this all in. All right, this is equal to the outer integral. If we do dz dr d theta, then I'm going to have 0 to 2 pi on the outermost integral. That's for theta. My middle integral will be for r. R goes from 0 to 2. My inner integral will be for z. Z goes from r squared to 8 minus r squared. And then xyz we found to be r squared z cosine of theta sine of theta. And then my dz, I have that. And then dA gives me an r. And now I have dz, dr, d theta. I need to recognize that I actually have r cubed in here, so I'll just rewrite one more time and then I should be good with this. This is equal to the integral from 0 to 2 pi, the integral from 0 to 2, the integral from r squared to 8 minus r squared of r cubed z cosine of theta sine of theta dz dr d theta. And that's it. And then we'll integrate all the parts. We can use that same sort of organization that we used in 15.6, where we identify the inner integral with the inner differential and call that A. You could do the middle integral with the middle differential and call that B. And then same for the outer and call that C. And then we can integrate one integral at a time. Each time we're calculating an integrand until we get our final number at the end. Okay? That's the gist of it. Now, I hope you noticed that it took us most of a page, more than half of a page, just to get this set up. So the setup really is kind of the hardest part. After that, it's just a matter of being really careful. And then, maybe any integration techniques that you might be struggling with. So if you do find yourself struggling, like, how do I handle this integral? Just reach out. I have no problem giving you any pointers you might need. Okay. The next example, we're asked to find the volume of the solid that lies within both the cylinder and the sphere using a triple integral. So the very first thing we have to remember is something that was talked about in 15.6. If we want the volume of a solid, the volume with the triple integral is just going to be the triple integral over E of 1 dV. Okay? The integrand is always 1 if we're calculating volumes with a triple integral. So our job is made a little bit simpler since the integrand is just 1. But we do have to deal with the bounds for our integrals. So we need to draw this. We have the solid that lies within both the cylinder and the sphere. Okay, let's see what that looks like. I'm going to draw a big ball for a sphere. Here's my sphere. Give it a belt so it looks three-dimensional. Okay, there we go. This is my sphere with a radius of 2. And then I'm going to draw a cylinder cutting through it. Okay. Now, they're saying we want the part that is inside the cylinder and the sphere. Okay, so that's going to be all this in here. You know what this is like? If you were to core an apple, we're calculating the volume of the core. And so what that looks like, if we draw it off to the side, I can make it a little bit easier to look at. So it is a cylinder, but then there's this rounded part on the outside because let's assume a perfectly spherical apple. It's rounded on the outside. And then same here on the top, we do have the top of the cylinder, but we also have the top that corresponds with the apple itself. Okay, maybe that middle part could be, hold on. There we go. Something like that. Okay, this is what we're calculating. Volume of this. Okay, so again, we need bounds for z, r, and theta. Notice that the top of this shape is coming from the sphere, not from the cylinder. And the top of a sphere, of this particular sphere, is z equals the square root of 4 minus x squared minus y squared. And then the bottom of this shape is z equals minus the square root of 4 minus x squared minus y squared. So all I'm doing is going to the sphere equation and solving for z. That gives me the equations of the top and the bottom parts of the sphere. Okay, that's not bad. I know that the cylinder itself has a radius of 1, and it's a full circle going around. We're not taking like a quarter of it. We weren't put into just one octant. We've got the full core. Okay, so let's see how we can deal with this. So this is the top of the sphere. We could say in cylindrical, this would be written as z equals the square root of 4 minus r squared. So I already know I need cylindrical, so I'm going to just go ahead and get it done. In the bottom one, this is the bottom half, or the bottom of the sphere. And so in cylindrical, we have z equals negative square root of 4 minus r squared. Okay. Then I can take my my circle from the cylinder itself. It's a unit circle. That's the projection of the cylinder onto the xy plane. It's just a circle. Okay, so if you were to look at like from the top and shine it down onto to see what the shadow is beneath, it's just a circle. And it's a full circle, so that means that r goes from 0 to 1 to take out the full unit circle, and theta is going from 0 to 2 pi. Okay, we often get 0 to 2 pi for theta unless we've been restricted to a particular octant. Okay, I think we have everything we need. We have the z bounds, the theta bounds, the r bounds. We know that the integrand is 1, and so I think we're good. Let's go ahead and set this up. Volume is triple integral. The outer integral, I'm going to go ahead and let that be my theta, so 0 to 2 pi. I'll let r be in the middle, 0 to 1. Z has to be first because it's in functions of r, and it'll go from minus square root of 4 minus r squared to positive square root of 4 minus r squared. And then we have 1. And then we have to remember that dv is equal to r dz dr d theta. So we'll put that in there. R dz dr d theta. Okay, that's not too bad. First things first, we would go ahead and take the integral with respect to z. We could call that a. Then we would deal with the middle one. That'll be b. And then we can deal with the last one. That'll be c for theta. Okay? In a, we're looking at the integral from minus square root 4 minus r squared to positive square root 4 minus r squared of r dz. This just gives me RZ from minus square root 4 minus r squared to positive square root 4 minus r squared. Leave the r on the outside. We're going to evaluate z now. It'll be square root 4 minus r squared minus a negative square root 4 minus r squared. So this gives me two of these. So this is equal to 2r square root 4 minus r squared. Okay, remember, this is the integrand for b. So with b, we're looking at the bounds of 0 to 1. We're going to be dealing with dr now. Our integrand is 2r square root 4 minus r squared dr. Looks like we have a u sub going on here. So the u sub, we're going to let u equal 4 minus r squared. Du is minus 2r dr. We don't have a minus, so I'll divide it over. Negative du will replace 2r dr. So now I'm looking at the negative integral of u to the 1/2 du, which gives us a negative 2/3 u to the 3/2 power. Okay, so I plug that in. I've got negative 2/3 times, instead of u, I'm putting in 4 minus r squared raised to the 3/2 power, going from 0 to 1. Okay, evaluating at 1, first we get negative 2/3 times 4 minus 1 squared is 3 to the 3/2, minus a negative, so it'll be plus 2/3. 4 minus 0 is just 4, so I have 4 to the 3/2. This simplifies. 3 to the 3/2 is 3 square root of 3. And then 4 to the 3/2, the half power means take a square root. So 4 to the square root is going to be 2. 2 cubed is 8. So I get plus 2/3 times 8. And then this simplifies to give me negative 2 square root 3 plus 16 over 3. This is my integrand for c. So now I go ahead and deal with c. C is where we're dealing with theta, 0 to 2 pi. Our integrand is a constant. It's just minus 2 square root 3 plus 16/3 d theta. And so we just get a theta out of that integration. I'm going to just change the order of these because I hate writing negatives first. So this is 16/3 minus 2 square root 3 times theta from 0 to 2 pi. And that gives me 2 pi times 16 over 3 minus 2 square root 3. This is an exact answer. Do not plug it in your calculator to get a decimal approximation because it'll get marked wrong on WebAssign, and that's super frustrating. So make sure you're good with keeping things as exact answers. All right, so that was a big one, right? We had to set up the integral using the shapes, come up with everything in cylindrical coordinates, finally get our volume, integral set up, and then the 3 integrals. All right, it's a lot of work. All right, we've got, it looks like, one more. So in this one, we're dealing with a solid E, and it lies within a cylinder, x squared plus y squared equals 1. And then below the plane, z equals 4. And above the paraboloid, z equals 1 minus x squared minus y squared. Wow. The density at any point is proportional to the distance from the axis of the cylinder. Wow. Okay, so this is a mass problem. Not a center of mass, thank goodness. But it is a mass problem, and we've got to get this shape figured out. So it's within the cylinder, below the plane, and above a paraboloid. Let's start with that paraboloid. Z equals 1 minus x squared minus y squared. That is an upside down paraboloid shifted up by 1. And it's a unit. So something like this. They all kind of look alike. That's my paraboloid. I'm going to put an octant on here. Okay, my shape is not in there. Let's see. If this is 1, let's call this up here 4. Okay, so up here we've got a plane. Let's see if I can draw that. There's my plane cutting through z equals 4. Maybe I could draw that a little better. There we go. Okay. Let's see. That's 2 of the things, z equals 4 and z equals 1 minus x squared minus y squared. Now what we have is a cylinder, okay? And the cylinder is, this is going to be fun. It is just as big as the paraboloid because it's a unit cylinder, and the paraboloid at the xy plane is also a unit. Okay, this is about as good as I can get, which I hope is good enough. We are looking at the region that is inside of this cylinder, not inside of the paraboloid. It is above the paraboloid. Do you see that? And it is below this plane. So this plane is up here in space. Okay? Goodness, that's hard. All right. Let's see. So from what I can tell, it looks like, you know, those cans that, like any can that you can buy that has like, it's like aerosol, and they're cylindrical in shape, and then you buy it, you bring it home, and you think, oh, I got this great big can, and then you turn it over and you realize that the bottom is inverted, and so there's actually less volume in your can than you thought because they inverted the whole bottom. It's not flat. That's what this is. That's totally what this is. So it looks like the bottom is this misshapen inversion, and it is z equals 1 minus x squared minus y squared. Wow. And then, so this is the floor. And then the ceiling is going to be this flat plane, z equals 4. So that gives me my z bounds. All right. And then the cylindrical shape, that's not changing, right? It's just its bottom and top that are different from each other. But the cylindrical shape is still like giving us our bounds for x and y. So if we project the cylinder onto the xy plane, we're going to get a unit circle. All right, we've dealt with these already before. And on a unit circle, we know that the radius is going from 0 to 1, and theta is going from 0 to 2 pi. Okay, that's not changing in this problem. Only thing changing is the floor and the ceiling. Okay, so that's going to take care of my bounds. So I'm going to just write these out. The lower bound for z, like in cylindrical. Lower bound for z is 1 minus r squared. The upper bound for z is still 4. Then we have r going between 0 and 1, and we have theta going between 0 and 2 pi. Okay, yay. We need an integrand. So for the integrand, we have a density function. The density at any point is proportional, that means it's equal to some k, to the distance from the axis of the cylinder. Okay, the axis of the cylinder is where x and y are 0. Okay, z is not 0 there. So let's see, if I was to pick any point in space right here, and I want to find the distance to the axis of the cylinder. The axis of our cylinder is the z-axis, okay? So this first point is x, y, z. And then this second point, because it is on the axis of, or the z-axis, it is actually 0, 0, z, okay? So actually, let me fix this really quick. This should be our row of x, y, z, since we are in 3D, and then it's kd, where the distance is equal to the square root of, and then we're going to look at the difference in the x's, difference in the y's, difference in the z's, and let's see, I want to say, yeah, okay, that works. So if I'm finding the distance between x and 0, it's going to be x minus 0 all squared plus, and then for the y components, it's y minus 0 all squared plus, and then for the z components, this is interesting, z minus z all squared. I know they're the same z because if I calculate the distance in space from a random xyz value to the axis, I'm going to stay at the same level. I'm not going to tilt my distance line. I'm going to go for the shortest line between my point and the z-axis. So my z values are equal. This simplifies to just be the square root of x squared. Square root of x squared plus y squared. Okay, which in cylindrical is equal to the square root of r squared. So this is cylindrical, which is equal to r. That means our integrand, which is our density function, and it's equal to kd, is equal to k times the radius. That's it. So now, I think I have everything I need. All right, we were told a long time ago that mass is equal to the however many integrals we need, and in this case, it's going to be a triple integral of rho of x, y, z dv. We have all of our bounds. We have our density function. We know that dv is equal to r dz dr d theta. So let's just put everything in. Our bounds, I'm going to stick with how I've been doing it. 0 to 2 pi goes on the outside, 0 to 1 in the middle, and my z bounds are going to be inside, and they're going to be 1 minus r squared up to 4. My integrand is kr, that's for the density function. My dv is r dz dr d theta, and that is going to give me the integral from 0 to 2 pi, the integral from 0 to 1, the integral from 1 minus r squared to 4 of kr squared dz dr d theta. And so we would do this very similar to how we've been doing things. We would go ahead and work with the inner integral first. That would be the a. We have the middle integral second. We have the outer integral third, and we could go ahead and integrate this. So if I start with a, I'm looking at the integral from 1 minus r squared to 4 of kr squared dz. K and r squared are both constants, so this becomes kr squared z from 1 minus r squared to 4. So that means we have kr squared, and then in my brackets I have 4 minus, in parentheses, 1 minus r squared. All right, kr squared times 3 plus r squared, which is going to be 3kr squared plus kr to the 4th power. So this is going to be the integrand for b. So with b, I have the integral from 0 to 1 of 3kr squared plus kr to the 4th. And now we're looking at dr. This gives me, now those k's, you know what, I'm going to pull those k's outside. And I'm looking at 3r squared. When I integrate that, I get 3 over 3r cubed, which is just r cubed. And I get plus 1/5 r to the 5th from 0 to 1. This, I'll leave the k on the outside. I get 1 plus 1/5 inside, which is 6/5 k. That is my integrand for theta. So my third and final integral, C, is the integral from 0 to 2 pi of 6/5 k d theta, gives me 6/5 k theta from 0 to 2 pi. Plugging into the 2 pi gives me 12 k pi over 5. That is the mass. That is our final answer. Okay, so there's been a lot to look at in these triple integrals with cylindrical coordinates. Hopefully it's been helpful. If you do have any questions at all, please reach out.